Hello, my name is Ryan, and I'm going to talk about XGBoost. XGBoost is a library in Python as well as multiple other languages. It is a framework created to solve machine learning problems. XGBoost has become a prominent machine learning framework as of recently due to participants in machine learning contests winning using this library. So, what makes XGBoost special? The primary concern of XGBoost as a library is to provide users with a machine learning system capable of utilizing all the computers or set of computers' resources in order to create and execute a model as fast as possible. XGBoost does this by utilizing these listed features. Parallelization and GPU support allow the library to access all the computer's resources in order to maximize processor speed. Cache optimization also improves speed through faster accessing. Since XGBoost is designed to work for large-scale systems and datasets, distributed computing allows for multiple computers to work on a single problem, and out-of-core computing allows for computers to pull from large datasets without having to put data in memory. With all of these features, XGBoost is able to solve problems dealing with regression, classification, ranking, and giving it the ability to solve a wide range of machine learning problems. XGBoost stands for extreme gradient boosting, but what is gradient boosting? Gradient boosting is a machine learning technique that utilizes gradient boosted trees, which can simply be thought of as binary decision trees with different weights on each leaf. The model is generated from a union of these trees, creating a precise decision tree from a number of more general decisions. In general, each individual tree is small, only going a few levels deep, but when combined, the model becomes much more nuanced and able to address a large number of features. This is a simple model outlining how these trees work. As seen in iteration 3, the model is composed of 3 binary decision trees with a depth of 1. While each one is simple, their union creates a much more precise result. Now we'll be talking about data structures and functions of the library that allow the user to create these machine learning models. Every data structure and function in the library contains a large number of getter and setter functions for each parameter, but these will not be addressed as they are self-explanatory and numerous. There are also a large number of parameters for each piece of the library, but due to the time constrictions, we may not be able to address all of them, as many of them are complicated and not very important. The primary data structure of the library is the D matrix. This structure is what is formatted data is placed into, and is what the prediction model is created from. There are a number of parameters shown here, but the only one required is data. Data accepts a variety of input formats as seen in the parentheses. While frameworks from libraries like NumPy and Pandas are recommended as data can be easily manipulated to the program, DM matrix also accepts input from files, with the string being used to indicate file path. XGBoost documentation recommends using libsvm text format files, but CSV files work just as well. First, the most important optional parameter is label. Simply, this designates which part of a dataset will be the result of the values, or rather distinguishes a result from input values to the model. XGBoost defaults to using the first column of a file as the label. However, most machine learning datasets, such as the ones from the UCI Machine Learning Repository, have the label column as the last of the file. Because of this, I would recommend manually setting the label for all datasets, as it is vital for the model performing well that this is correctly set. For incomplete datasets, missing or replace values with the decided number, defaulting to none if not set. Weight allows the user to manually determine the weight of each instance, like missing it will manually default, meaning that it should only be altered if the user knows what they're doing. Silence simply determines whether or not data structure should be printed message during construction, defaulting to not printing messages. Feature names and feature types both take in lists of parameters and are used to organize the D matrix. Setting these is important for readability and understanding the object, thus it has no effect on the actual performance of the model. Finally, nthread determines the number of threads used, but only if the data is in the form of a NumPy array. The other important data structure in the library is the booster. While DM matrix is used to load set for creating a model, booster is where the completed model is stored. While booster can be created as an independent object, it will primarily not be used this way, but rather as a return value from the training method that will be discussed later. The model is capable of storing a trained model, and then using it to make predictions on data and provide other statistics. The param section of the parameters list will be covered later, as is utilized in other methods but not specifically relevant here. The only case in which a user would create an independent booster object would be willing from a file, as a booster can only be saved in a file to avoid recreating it on each program run. However, the main purpose of the booster model is the predict function, which is used model associated with the object on an input data set to return predictions. There are a number of optional parameters available for the function, but likely the most important is the n-tree limit, which will allow the user to determine the maximum number of trees in the prediction. This is important as a big problem in designing machine learning models is overfitting and underfitting data. This is a problem caused by a model being too general or too specific to utilize a wide range of data, leading to inaccuracies in predictions. Since the complexity of the model is tied to the number of trees used in the ensemble, n-tree limit gives the option to reduce the complexity by limiting the number of trees used in the model, fixing the problem of overfitting. This covers both the core data structures for the library, and we may now look at the methods that are used in the data structures. Primary method of the library is train, which will be used to train a model for the DM matrix object. As mentioned before, a booster is returned from the function, which is what contains the train model. This function has a large number of parameters, so much so that the dictionary of parameters is passed as a parameter into the function, allowing for complete customization over how the model is trained. This is important as there are a variety of parameters that are vital to how the model functions, making it important to have complete control over how the training model is generated. As the most important, we will start with params. As mentioned, this is a dictionary of values used precisely to a model, and it is important to understand at least the vital parts of a dictionary if you want to create a working model. To begin, we will address the general parameters of the dictionary. These are all relevant to the model regardless of what kind of machine learning task is being performed. First is verbosity, which is similar to sound function present in D-matrix structure, allowing different levels of information to be printed. Similar to D-matrix parameter, n thread determines the number of parallel threads used to instruct a model. What is likely the most important optional parameter is the booster parameter. There are 3 selections for this, but each one must significantly alter the way the model is generated. Each model has its own set of subparameters, meaning that some of these must be addressed depending on the selection made here. GB tree and GB linear are both gradient boosted models, but GB tree uses a tree model with GB linear functions. JART is another tree model, but will provide additional parameters on top of the parameters of the GB booster. Any of these additional parameters will be addressed starting with the GB tree booster. What is likely the most important parameter for tree models is the ETA. This value is simply a float in the range 0 to 1 defaulting at 0.3, where rates for the trees are reduced by the value after each boosting step. The result of this is that the steps become more conservative, meaning that it will not make such precise decisions in every tree in the final model. As mentioned before, a big goal is to avoid overfitting a tree for a specific data set, as this is ruin the model when new data is introduced. Another important parameter for preventing overfitting is max depth. This simply determines the length or the depth of each boosted tree in the ensemble will have, allowing for greater control over how the model is generated. Next are a few more simple parameters. All 4 of these parameters affect how conservative the tree is, making them important for preventing overfitting. For time reasons, I will not cover them, but know that they all affect conservation. The tree method is used to determine how the tree is constructed, and is another important feature of XGBoost as it specializes in speed. As seen, auto-selecting an algorithm that results in the fastest construction based on the dataset used. Because of this, it is likely the user want to keep this value as default. However, as you can see, there are other parameters there if you want to use those. The next parameter is updater, which is actually another parameter listed within the current one. This parameter tells the model constructor specific updaters to run when constructing a tree. There are a number of them, but the defaults will be grow column maker, which sets columns-based construction of trees, and prune, which removes splits on individual trees depending on whether or not it is lower than the aforementioned gamma value. As mentioned before, there's a second kind of tree booster in the tree construction, which is the dart booster. A dart booster executes what is called a dropout, in which during prediction some trees will not be evaluated, so these parameters affect the mechanism of the booster. For time reasons, I will not discuss these parameters, but here are what they are. Now we will cover the additional parameters for the linear booster. To start, the lambda and alpha parameters turn and function is basically the same way as the tree booster. Next, updater determines the algorithm fitting the linear model. The final parameter for linear booster is feature selector, which determines how features are selected in the construction of the model. Features are an important part of the model as they refer to the individual data points being used to make the prediction. For time reasons, I will not go into detail on the specifics of each of these methods, but they all act as their names entail. With that, the additional parameters of the models are finished. The final and potentially most important piece of the parameters list is the objective. Simply, this determines the kind of algorithm that will be applied to datasets. While the actual algorithm is important in producing the model, the most important thing is to note the user is the label before the column of each type. This label refers to the kind of problem that this algorithm is used to store. This is important because in order to create at least a basic model for a dataset, we must know what kind of problem the dataset is addressing. Reg refers to regression, which is used to the outcome predicted as a number. Models that require some number to be calculated must use the objective, as other objectives are not designed to produce the same result. Binary refers to binary classification, in which the output is one of 2 classes, such as true or false. Multi refers to multiple classification, which is classification problems like binary classification, but with more than 2 classes. Rank refers to learning to rank problems, in which the model must order some dataset in a way similar to ranking. These 3 types of objectives, regression, classification, and rank, are what XGBoost is capable of performing. While the actual algorithm such as linear or logistic that is performed is important, it is much more important to ensure that an objective that corresponds with your type of analysis is selected. Because of this, I will not go into further detail about the algorithms associated with each objective, but know that there is still important to choose the one best suited to your problem. With that, we are finished looking at parameters listed for the train method, and we now look at the remaining parameters. Detrain is the only other required parameter, as it is a set of training data that will use in the data. Num-boost rounds determine the number of boosting rounds performed when training data. Each boosting round will further improve the model, but will obviously require more time, which is why the default value is set to 10. Evals takes an interesting type of list of the matrix and string tuples. The item passed are evaluated during the training, with the purpose of letting the user see how they perform against the validation set. This is another feature that helps the user determine how their model is performing. To pair with evals result stores the result from the previously passed items in the dictionary that can be accessed from the booster, allowing the user to access the data. The final piece of the eval section is verbose eval, which provides immediate feedback on the values of eval during the construction of the booster, if said true. It can also be further tuned to print every X number of stages, giving further feedback. Obj and feval allow custom objective and evaluation functions to be passed into the function called default if number pass. Maximize works with feval and will determine whether or not maximize the feval function. Finally, callbacks is a list that determines the callback functions performed after each iteration. There are 4 total callback functions that will be shown now. The first 2 callback functions are in relation to the evals discussed before. Something to note is that these callbacks actually produce a function that returns the result rather than the direct result. Functions also have parameters, but they will not be looked at in detail. These 2 functions are quite simple, as they either directly print the result or they save the result into the eval list parameter. The set learning rates refers to the aforementioned ETA parameter in training, which also refers to learning rate. This callback will affect the ETA value after iteration 1, depending on whether or not the learning rate parameter is a function or a list. Next, early stopping involves another feature of XGBoost, which is early stopping. Early stopping is also linked with the evals parameter and will cause the model to stop training if the validation error generated from evals validation stops decreasing between some set of number of rounds. To think of it simply, this callback will provide a function that stops the training if it has seen the model is not getting any more accurate, saving the user time that would have been wasted. The first of the final parameters of the train is XGBModel, which allows the train to continue from an already completed model. This would be useful if it's seen the model cannot fully fit and must continue the train to be successful. Finally, early stopping rounds determines the number of rounds in which the validation error must decrease for the train to continue, but will also contain additional data if early stopping is activated, as seen there. The final function of XGBoost library is CV, which allows cross-validation on dataset. The params list is identical to the one found in training, but with the normal function parameters being altered. Since it's not a function needed to create a model, I will not discuss it any further, but more can be found in the documentation. We have covered the primary components of XGBoost library, but it also contains some components that are not native to XGBoost, but are adapted to work with XGBoost speed and increased features. Since they are not technically XGBoost, but rather other libraries linked with XGBoost, they will not be covered in too much depth. Scikit-learn is another powerful Python library for machine learning, but its basic components are included in XGBoost library. The API actually has 3 separate calls for each type of machine learning problem it can address in the form of requester, classifier, and ranker object. Each of these functions is similar to learn, except for the params list as well params similar normal training parameters. However, where train looks like the type of problem, the objective label of params, scikit-learns primarily classifies it by the function call itself. Fit is the function that fits the model data, similar to how train works, and finally predict is the predict function, which is used to actually produce the results for a model. XGBoost also includes parts from matplotlib, allowing the user to plot a data generated by models. As seen, it includes 3 functions that allow you to plot importance, a specified trigger booster, or convert a tree into a graph viz instance. All 3 of these return the same data type and can be used to further system analysis. With that done, I'd like to quickly example of rote to show off some points about how to do things here. So this is the full code, as you can see, and so I think this is worked off an example from the learning XGBoost. So basically, it's taking a data set of poker hands, and it's determining the kind of hand you have based on the cards in the hand. So we'll go ahead and we'll look at each kind of point here in the thing. So first of all, you have to import, obviously, and I'm using NumPy to take in the data here. So taking the data, so you need to train a test set with 80% of the data being in train and then 20% being in test. There you have to split it. So here I get the labels out, and so you can see the last column is the label, so I set that as the label, and the rest is the data. And then XGB train, we put them in DM matrix for both the train and test. Then we get the parameters list here, and you can see we're using multi because we're using multiple classification and with 10 classes total. Finally, we create a boost and make a prediction with that boost and print out the error. And then to test that, we actually use a different objective here and then make another prediction and print the error out again. And as you can see, the error does change with the objective, so choosing is important. So in conclusion, gradient boosting is for speed and efficiency. That's probably what it's for. So it's definitely a very powerful library, and it can address these multiple problem types of regression, classification, and ranking. It also includes scikit-learning with the increased speed, which is always good. And then finally, for creating your own XGBoost model, that's the basic structure: D-matrix, train, booster, and then predict. Any further questions, or if you want to look further into it, this is the documentation for XGBoost. Thank you.